Welcome back. I hope you are liking this course so far. In the previous lesson, we looked at how to train machine learning models and graph neural networks in PyTorch. In this lesson, we'll see how to modify those existing models that we trained and create new model architectures and train them. Let's jump right in. So machine learning models are present in a lot of packages, and there's no need of us to create one. And for chemistry, we can use the existing models which have been applied elsewhere and see how good they are for our application and purpose. In this lesson, we'll be using models from DGL and make slight changes to the models as we see fit, and then use those models on the QM9 dataset and do predictions on the HOMO property, the HOMO-LUMO gap instead. So at first, let's start by installing the packages, the DGL Live, RDKit, FastML. Now I have already installed the packages here, so let's just jump into the code for training. So this is the code that we have looked at so far in the previous lessons, where we load the pandas data frame from the for the QM9 dataset, take smiles, and we featureize them. We'll be looking at modifying a graph neural network, the MPNN that we used in the previous lesson. And so we have graph featureizers for that, and then we have smiles to graph, and all of this code was used in the previous lessons, so it just copy pasted in a single cell here. And we have batch loaders and train, valid, and test loaders, and finally the loss function. Let's just run this code, and it should be quick because we are not training anything, and we have a fraction of a big data set. Once it is done, it should let us know it's done. It should be quick. And then in the following cell, I have created a function for running the training and validation. Instead of using a for loop, this is a function that gets in the model, optimizer, loss, train data loader, and valid data loader, and runs the training. So this is the training loop, but I have set it to 1 epoch, as we just want to check whether the model works or not. And as we saw in the previous lesson, it takes about 5 minutes or so to run the actual code. So we'll just run 1 epoch and make sure that it runs. And we have epoch within the epochs, we have model training, loss, and the earlier stuff that we saw of model getting features. We also have the validation batches, and we compute the loss at for each of the batch that goes through. So let's just run this helper function. So we have it ready, and before running the model with modified architecture, let's train the default one, and let's see how that goes. So we'll import the MPNN predictor as before, and set in the parameters here, and this is the Adam optimizer that is used, and we are training the model. This is just for 1 epoch, so it should take a minute or so to run, and it should prevent the validation loss and also the training loss. This is just to check whether everything is okay, because we'll be using the data loaders that we have in training the other model, which will be modified version of this MPNN. Let's wait for a few more seconds. Hopefully it should be quick. So here we have our training loss and validation loss. So 1 epoch is done. That's all good. So let's see how to change the code. Okay. So this is the MPNN predictor from the DGL Life library, and this is the entire code in the file, in the corresponding Python file. So we have an MPNN predictor class, and these are the import functions on top, and there's the description for parameters that are used in this. So the class has two things. One is the init function, which takes in all of these node features and everything, and then there is the forward function. So we'll look at how to make changes to both forward and the init function, and when to make changes for both of those. At first, let's see what the init function looks like. So this is the function that creates the model architecture, and within this model architecture we have the GNN part, which does the graph neural network, and from the graph neural network we get transformed graphs out of it, which are then read out with this set-to-set function. And the set-to-set function is a way of converting the graphs into a vector, and that vector is then fed into this predict layer, which is a sequential run of something. And this nn.sequential means that whatever is inside this is run sequentially. So first we have a linear layer, and that is the linear function, and then you impose the non-linearity with the ReLU function, and finally you have another layer that takes in the input from the ReLU and gives us an output. And you see there are two layers with the ReLU function, and that is what is the architecture of the model. I would like to note that these set-to-set and MP NNGNN are also neural networks within this neural network, and you could just use the MPNN class itself and see how that works if you look into the code definition for these two models. And once everything is set, the forward function is actually what we give the model inputs for, and I'll show you how this looks in the training or the validation code. So forward is what takes in the graphs, the node features, and the edge features. And if you are writing a code for training or validation, this is the function that you need to look at within the model and see what it needs. And in this case, graph features, node features, and edge features. So once it has those graph features, edge features, and node features, this is the code it's working. So at first, it takes in the graph, node, and edge features and passes it into the self GNN. And what this corresponds to is the function on top here. So it is using this neural network, and these features that you see in here are the ones that are responsible for creating this network. But if you look at the code for the MPGNN and look at the forward part of it, and this is what it will look like in the forward part. So it would still need G node features and edge features. So we pass that to the GNN, and that gives us node features as the output. And the node features are then put into the readout function, and the readout over here is set to a neural network, and that neural network in the forward method for the set to set would require the graphs and the node features. That's why we put in graphs and the nodes that we get from there, and it gives us the graph features. And finally, these graph features are put into this predict function, and you can look at the dimensions of those features here. So it's twice, and node out features is what the readout function gives us, and that is then given into a hidden layer, which is node out features. This is the number of neurons that it contains in that layer, and from there on you pass it on to the final linear layer, which is n out features, and that then transforms into number of tasks. In our case it's 1, so this n node features would be finally giving us 1 output from these node features. And that's how this entire functions work, or the model architecture looks like. And so if you want to make any changes, so if you want to replace GNN with something else, we just replace this code. We can replace the readouts, or we can replace the predict part of it. So in this lesson, firstly we'll look at how to change the predict part of it. And if you look at the predict part on top, it has a linear layer value and another linear layer. So let's say we want to add linear layers here and another value. So let's see how we can do it. Okay, so and that is the task, adding a linear layer and a value layer to the predictions. So at first, let's look at this code. What we are going to do is we'll do the same imports as before, because we need all those set to set functions, mp and n's, and also torch and then we'll copy the same parameters for the init function, and I would say entirely copy paste the function, that the class that you see above, into this. And now we need to change the predict part, right? So within the predict, let's say we want to add the linear function after the value. So we'll do nn linear, and the linear function needs a input and the output. So the input for this should be, so the input for this layer should be the output for this layer, and that is n node feeds. So that is the number of neurons that you need in that layer. So let's see how many neurons are set in this case. So node out feature is set to 64. So this would be 64 dimensional, and there would be 64 neurons, and so we would want that to go into 64 neurons because we don't have any other operations in there. So we can say, okay, that features, and we know that node out feature was already set before. We can put the output for this layer to be node out features, or we can make it twice node out features if you want here, and make sure that this corresponds to this again, so you can have again 2 times node features. Even this thing should work, and this is the only change that you're going to make because we wanted to make change to this layer. You can see how it works, and there's no change in the forward layer because we just passed the graph features into the prediction layer, and prediction layer doesn't need any additional input, so we just use the previous input itself. So let's just run this code and make sure that you change the name if you are using the MPNN. So I call it MPNN modified, and you also need to change the name over here, and let's just run this code. So we have created the class MPNN modified, which is a machine learning model architecture. So as before, we could use the same parameters, so in feet, node feet, and everything. There's no change in the model itself in the init function, so initialization is the same, and we can run this. We'll use the optimizer, which is the Adam optimizer, and this should start training the model, and we'll see what it looks like. And hopefully if it's running, it means that the code is working. And if you want to look at what the model looks like, we'll do it once this code is completed. We can look at the model, and we should be able to see that additional layers have been added to the predict function here. So we'll wait for the completion of this. Now that this is completed, we can be sure that the code is working right now, and everything is looking good. if you want to look at the model, you can just print this model as before as model, and I'll show that in the next model that we are going to do. So let's say now, instead of adding the number of layers, we want to make a little bit change in the initialization part. We in the previous model added one layer to it, but what if we want the model to accept an input from a user and add those many number of linear layers followed by a value? Suppose if I give it an input num linear layers, and if I say, okay, I want number of linear layers is to 1, so it'll add one linear layer in the predict function. If I say linear layer equal to 3, it'll add 3 linear layers, and each linear layer would be followed by a value function. And let's see what changes do we need to make if we need to do something like that. So again, copying the entire code into this, we would need to add this additional thing, which is number of linear layers. Earlier we didn't have that argument to this function, so we would need to add in that argument, and this function remains as it is. We are still using the mp and ngnn and set to set. Now if you want to add number of linear layers followed by a value, a easy thing to do would be to use a for loop in that case. So what I'm doing over here is, let's say the number of layers is equal to a list. So this is a placeholder where we can add the number of layers and a value into it, and then we'll finally convert it into a model. So based on the number of layers the user requests, we can create those many number of linear and values. There's a for loop and add those things. So if we have two number of linear layers requested, so there'll be one value followed by a one linear followed by a value, another linear followed by a value. So once that is done, we have layers set into the number of layers that we need, and to add those into the function, we would just need to do nn sequential and the number of layers. What the nn sequential does, it's whatever is inside, as I mentioned before, it runs it sequentially. So it goes from linear to value to sequential again, and then sequentially runs whatever is inside, and it'll be nn value, and then followed by again nn linear followed by a value. And if there are multiple linear layers requested, that value will again be followed by linear and value, and so on and so forth. So once that is done, we'll finally have the number of linear layers and the tasks. Again, I would like to mention that the input features are again crucial. So you need to make sure that the next layer has the same output feature as the previous layer, and the input matches the output of the previous layer, as I discussed previously. So this should match the previous one, this should match the next layer this should be the output should be the input for the next layer, this should be the output of the previous layer. And these are just dimensions for linear layers. So once we have that, there's no change in this part because we are still passing in the graph features into this predict function, and only thing that we are changing is this part. So there's no need of changing the forward function, but do note that we have added a parameter in the initialization which wasn't there in the previous model that we trained. So we can even change, so this is to demonstrate we can add a parameter over there. And let's just create this ML model. So this model is ready, so let's add in all of these arguments. And if you look at the predict layer now, so we have a linear layer 128, output is 64 features, and then that is passed to the sequential layer that we added. And because number of layers is set to 1, we just have one linear followed by a value, and 64, and that 64 is same as the input for this, and output is 1 because that's the number of tasks that we have, and we are just predicting the gap. So if you want to add more layers, let's say we set that to 3 and run it, we will see that we have added this is the original model, but sequential is what we have added now. So we have linear, value, linear, value, linear, and value. So we added it 3 times, and the output feature matches the input of the next layer, and the input matches the outputs. So this is good. So let's try to train this model and see whether the model works, and it'll take a while to load train it on the entire data set and see which model is better, whether 3 layers are better in this or 2 layers are better. But this is just to demonstrate how to change the code. But you are welcome to load the entire data set and train the model and see how it works. So let's run this code again with this model using 3 linear layers and see whether it prints out something. Okay, so the model training is over, and we see that it does work. We have training and validation. So the changed model works to some extent, but we are not sure how good the model is. For that, you need to train the model for longer epochs and use a little bit larger chunk of the data set. So in both of these examples, we looked at changing the init function in the model class, and now we'll see how to change the forward function of the class and what could be the reason of changing the forward function. So this is a figure from one of the published articles where they found out that you could use a molecule and use the learned representation. So learned representation is from the graph neural network, and then do a property prediction. But if you put in some fixed descriptors or fingerprints and add it to the learned representation, that would significantly improve the property prediction. So the model architecture over here remains the same, but for final prediction, we need to add in descriptors or fingerprints into that learned representation that we get. So let's see how to do some modifications like this, and these modifications would be done in the forward function. So I copy pasted the entire code over here, and we still call it NN modified, and this is the initial code, the default code that we have in the DGL, and because of that we don't have any additional layers added or anything. So we have the where did it go? Let's see. So we have the MPN and GNN, the set to set, and sequential with one linear, a value, and a linear. So there is no change in the init part of it because the model is not changing at this point. But what is changing is the predict layer should get the descriptors or fingerprints into it, and we'll have some proxy for this. We won't do the exact descriptors or fingerprints. We'll just take in some a vector and then do it over here. Add it to the learned representation. So if you want to add it to the learned representation, we need to do it in this case in the forward function. So graph feeds are the readout from the GNN, and these features we need to add some features to this and then do the prediction. That's what the article talked about. So we have, this is the learned representation, so you can add the features into it and then do some prediction. And to do that, what we will do is we need something added to it. So in this case, we'll just say it's a constant that we are multiplying it with, just as a proxy. We could do the entire descriptor and other things, but it would take a lot of time. But as a demonstration, I'll just show you how we can take an input here and make changes to this function. So let's just multiply the features by a constant here. So if you want to do that, we have the graph features. So just as a just to show that this thing works, I would say old features, it'll print the old graph features. And then for the new graph features, what I need is I need to use these graph features and then multiply it with a constant or any vectors or any tensors in here. So this operation over here should be a tensor operation, and it should not be just multiplication of numbers, but it should be multiplication of tensors. So if you have any features you want to concatenate to this, you would concatenate two tensors and try to use the corresponding function that does concatenation. In this case, I'm multiplying it with a constant, so I have the multiplication operator here, followed by torch.tensor and then constant. So the constant the user provides will be multiplied by the graph features, and that graph features will then be used in the predict function. And to show that the feature indeed that has changed, okay, so this code should be new graph features here, and to show that this indeed works, we'll show the old one, the new one, and the new one is what is going into the predict, and the prediction is made from the new features. So let's run this model, and it's ready. So when we create the model, you won't see any changes in the model. So we have the GNN, we have predict with one linear, one value and another linear. The things are changed in the forward function, so we'll need to change the valid and training that on the helper function that we created, because the forward function now not only requires the graphs, node features and edge features, it also needs a constant. But if you look at the code that we had above, we only provided the model with these for training and validation. So now we would need to add a constant in there too for training and validation or testing everything. So to do that, we have another helper function, same as before, but now we would need to change this. So we had graph features, node features, edge features, and then we need a constant. Let's say we just multiply it by 10. So all the features that we see should be multiplied by 10 in the training, or also we should see that over here in the validation too. Okay, so we have 10 added in here. So once we run this function is ready to be used, and we'll add the optimizer and model, and let's see what it looks like. It should print out a bunch of old tensors. So old tensor is the one that it got from the readout layer, and readout was 0.04, and if we see the new tensor, it should be 10 times of that, and you see over here it's 0.43. The old tensor was 0.043. So we see that we are able to successfully do the tensor operation in the forward model, in the forward function of the model. And this was just a multiplication, but you could do other operations in there, like concatenation, or you can have some convolution or other things put in there. And even if you change, for instance, the model itself, let's say you changed the model over here. So instead of sequential, the predict sequential, it needs some other model, or in case of readout, it's not set to set and it needs something else. and the forward part of it also changes. In that case, you would need again to change. Let's see whether I can reach the code. Yeah, so over here, so if you change the GNN and it needs some other features inputted in, or if you change the readout, it needs some other features, you need to make sure that those features are mentioned here, and you use those in the model training, and then pass it on to this, and it should be training the model. And that's how you see that this model is being trained, and there'll be a lot of outputs in there, but hopefully we'll see the validation losses this. So it's working on both training and validation, and we can see the old tensors and new tensors are very different. So I hope that with this you would be able to change any models and see how the model performs with the parameters that you put in, and also look at the forward, the initialization, or play around or tweak around with these kind of things. I will see you in the next lesson.